Alright, welcome back. One more time we're going to take a look at compositions of functions. This time we're going to use some graphical representation to help us look at these a little bit differently. Even some of the equations that I go over here in the notes, we're going to take a look at them through Desmos tomorrow so you can get a clear picture of why it is the domain restrictions were what they were on each one of these functions. Alright, so we're going to use these two graphs to help us with the first set of examples. Simply, you're going to determine which value of x and corresponding y value you have, and then later on we're going to use those combinations together to figure out what our compositions of functions is. Alright, so in answer choice A, we have f of 0. That means when x equals 0, the corresponding y value is 8. F of 3, when x equals 3, the corresponding y value is negative 1. G of 4, now we're moving over to this graph. G of 4 is out here. When x equals 4, the graph is undefined. Therefore, one term we can use is DNE does not exist. Now we're going to get into the compositions portion of this activity, so take a look at this carefully. First thing I do with compositions of functions is work from the inside to the outside. So it's a two-step problem. The first thing I have to find is what g of 0 is. So when x equals 0, y equals 2. This is the part from the definition yesterday where you take a look at this output and you place it as the input of the second function. So now I need to determine what f of 2 is. Coming back to the f function, when x equals 2, y equals 0. So the answer of f of g of 0 is 0. Again, this two-step process, we start from the inside out. G of negative 1 equals. So when x equals negative 1, y equals 1.5. I'm going to take that output and place it as the input of the f function. When x equals 1.5, y also equals 1.5. In this particular problem, we start with the f function, f of 2. When x equals 2, y equals 0. I'm going to take that output, I'm going to substitute it into the input of the second function, g of 0. So when g of 0 is 2. Okay, this one's a little bit tricky. It's actually working backwards through all of our problems. We have a final answer of 8, and we're trying to figure out what the original x was to get that final answer of 8. So now we're going to work from the outside in since we're working backwards. That means that the end y value, the end output is 8. I'm trying to figure out what f of x is when y equals 8. Or I'm trying to figure out what x is when f of x equals 8. So I go to the f function, I go up here to the y value of 8, and I look for the corresponding x value, which in this particular case is x equals 0. I'm going to take that number, and that value right there becomes the new output. So that means g of x equals 0. Remember, working backwards here, so this number becomes another output, not another input. Now I'm going to go to the g function. I'm going to find the y value of 0. So I notice in this particular instance that when y is 0, x could be this number, or it could be that one. So that means in this particular case, there are two possible solutions to this problem. X could be 2, or it could be negative 1.5. Alright, is it possible for g of f of x to equal negative 3. Okay, so again, we're going to work backwards on this one and figure it out. So I'm looking for g of x when y equals negative 3. So I come all the way over here to where y is down here to where y is negative 3. I notice immediately that there is no corresponding x value, so the solution to this problem is no, it's not possible. And the reason is because there is no corresponding x value. At g of x equals negative 3. Okay, now we're going to get into some of these compositions of functions using actual functions. Now, as it turns out, there's a relationship between compositions of functions and inverses. Very important one, actually. It makes it very easy for you to determine whether or not two functions are inverses of each other. You simply insert one function into the other. It doesn't matter which order you do this in, and the output will always be x. So the way that you determine whether or not two functions are inverses of each other is by inserting one into the other, and the solution that you should get is x. So here's how that works. Based on the way I wrote this, I'm going to substitute the g of x function into the x value of the f function. So it looks like this. 4 times 1/4 x plus 1, there's the substitution, minus 4. Using the distributive property here, I get x plus 4, and then I add on the minus 4 to the end. 4 minus 4 is 0. Therefore, the resulting answer to this problem is simply x, which means yes, these two functions are inverses of each other. Let's take a look at another example so you can see it one more time. Again, it doesn't matter the order that you insert one into the other, but the output is always going to be x if the two functions are inverses of each other. So, negative 1/3, here's the substitution, 3x minus 3 minus 1. The distributive property will give me negative x plus 1 minus 1. The ones cancel, giving me the result of negative x. And the answer to this question is no. These functions are not inverses of each other because the resulting output is not positive x. Alright, in examples 4 and examples 5, these are the two that I'm going to show you tomorrow on the Desmos program so you can see visually how I found the restricted domain of each of them. We've also introduced a new set of composition symbols. So this open circle here, it is not a multiplication sign, it is not an excluded value, it is the same as writing f of g of x. So if you are confused, just rewrite it automatically like this, and it keeps it consistent with what you've seen so far. Okay? Now what we're going to do here is we're going to substitute the g function into the f function, and it looks like this. Now, because the square root function has a restriction, that means that there will be a restriction on the composition of functions. Please understand that yes, these two functions are going to cancel each other out, the square and the square root, leaving a linear function. But because the original function, the square root function, had a restriction, the composition of functions will have a restriction also. That means even though the final answer to this is x minus 1, it still carries the restriction of x must be greater than or equal to 0. Be very careful about that. We'll see that again later on in the school year. Okay? The other way around, we have the square root of x squared minus 1. Now what we're going to look at is we're going to look at all of the values that make the radicand a negative number. Okay? So anything that is smaller than the positive value of 1 is going to give me a negative value, because 1 minus 1 is 0. But 1/2 minus 1 gives me a result of negative 1/2. So this is a very important concept, because there's actually a range of values that fit this criteria. So any number between negative 1 and 1 are undefined. So please understand that this list of values is going to be what you use. Now it's going to be easiest for me to use interval notation on this, because all other values are defined in this particular domain. And that's going to be your restricted domain there. Alright, again, if you're confused, f of g of x looks like this, and g of f of x looks like this. Alright, so we're going to substitute first the g into the f, and it's 3 times the square root of x minus 2 plus 1. In this particular case, it's just that number right there that does the restricting, so it's going to be x must be greater than or equal to 2. Likewise, over here, I'm going to substitute the f function into the g function, and I get 3x plus 1 minus 2. Combine like terms, and I get the square root of 3x minus 1. This restriction right here, x must be greater than or equal to positive 1/3. We're going to take a look at these visually tomorrow. If you're curious about them now, go ahead and graph them in your calculator, and you'll see some of these restrictions take place. Alright, the extension question. I'm really curious to see how you guys are grasping the concept of compositions of functions. If this is your function, I'm going to substitute a plus h into this function first, then simply a, and then finally h in the bottom. So take a look at this one, go ahead and try to do your compositions of functions, and let's see how many of you can get the final simplified form of this particular function.